So this is first part of Unit 1. Unit 1 is dealing with measurements, and as we covered in the lecture on what is science and the scientific method, I spent a good deal of time talking about how science, they do experiments, they make observations, and part of those observations are measurements. And the thing about measurements is measurements are quantitative. Okay, so there's two types of data. There's qualitative and quantitative. Right? So up here where it says quantitative, you think quantities. So in quantities we're talking about how much or how long, how much time. Qualitative doesn't really put numbers to things. So they may, what color is it, blue or red? Or was there an odor? Was it a sharp odor? Was it a pleasant odor? Was it a noxious odor? Was the texture rough or smooth? Did the reaction occur fast or slow? That sort of thing. Most of those qualitative measurements can be quantified. So down here, many qualitative data can be quantified. So color, we can talk about the wavelength of light. Odor, we don't really have a good way of quantitating that yet. But certainly was a reaction fast or slow, we're measuring time. So we can, measure how much product was produced per unit time, that sort of thing. In any event, quantitative measurements require numbers. So we have to be able to deal with numbers, and so there's, at least in the first unit here, there's quite a bit of math. The thing about these measurements are they're reproducible. We talked a bit about precision before. We'll talk more about it in this lecture. Was the measurement precise? Which means was it reproducible? And it's not necessarily reproducible just by you in your own laboratory, in your own experiment, but by others. So the measurement should be independent of the observer, which is why we would want to say quantitate or quantify color, for example, because what might be blue to you might be more purple to someone else. So it's important to quantitate things so that 4 is a 4. It doesn't matter if it's your 4 is the same as my 4, your 8 is the same as my 8, and so forth. So it's independent of the observer. The really neat thing about these measurements, it allows us to predict the future. So using formulas and calculations, I can actually calculate how long it's going to take for a certain object to fall, or I can calculate how long it's going to take for a certain reaction to come to completion, and that sort of thing. So by quantitative measurements, it allows reproducibility and prediction of the future. Now in chemistry, actually in chemistry and physics, other branches as well, they tend to involve either very large numbers or very, very small numbers. Some numbers, such as this is 1 trillion, right? A lot of zeros here, and it would be real easy to miss a 0 or 2, and if you do, you're not off just by a little bit, you're off by a factor of 10 or more. So it's a lot easier to write large numbers like this in what we call scientific notation, or powers of 10. And it's really just a convenient way of keeping track of zeros. I say here zeros because if you notice here, there's 3, 6, 9, 12 zeros. This is 10 to the 12th. The exponent here, 10 to the 12th, is the same as the number of zeros. More accurately, it would be to say that this is a way of keeping track of decimal places. But if you want, you can think of keeping track of zeros. So if you notice, alright, so if you're 10 squared, alright, so 10 squared, what is 10 squared? 10 squared is 10 times 10, right? 10 times 10 is 100. 100 has 2 zeros. There's a 2 here. 10 times 10 times 10 is 10 cubed, 10 to the 3rd power. That has 3 zeros. And you can keep going on all the way up to 10 to the 12th if you like. 10 to the 1, this is simply 10. It's a 1 with, you guessed it, 1 0. 1, how many zeros do you see here? There's 0, 0. So 10 to the 0 is 1. And it turns out that we're only going to be dealing with powers of 10, but it turns out that anything to the 0 power is 1. Okay? 10 to the 0 clearly is 1 because it's a 1 with no zeros. Then we get to these negative numbers. So 10 to the minus 1, what does that mean? Well, x to the minus 1 means 1 over x. Okay, so this is a reciprocal. Okay, so when you include this negative sign here, what you're saying is don't just take x, take the reciprocal, or 1 over x. So if we have 10 to the minus 1, what is that? 10 to the minus 1 is 1 over 10, the decimal equivalent of which is 0.1. Right? We can do the same thing here. 10 to the negative 2, well, what is that? Here I have the decimal equivalent is 0.01 or 1/100th. Where do we get that? Well, 10 to the minus 2 is 1 over 10 squared, right? The exponent is 2, and the negative sign means we take the reciprocal. So 1 over 10 to the 2. 1 over the 10 to the 2 is 1 over 100. The decimal equivalent is 0.01. Now it's true that, let me write this here, 0.1 is the same as 0.1. 0.01 is the same as 0.01. So you notice if you include these leading zeros, the 0 before the decimal point, right, then the number of zeros here also equals the exponent, except that they're fractions, right? So 10 to the minus 1, 0.1. 10 to the minus 2, 2 zeros, 0.02. Right? Another important thing to notice here is large numbers. Numbers larger than 1 are going to have positive exponents. And of course, well, small numbers, those that are fractions, those are less than 1. Small numbers have negative exponents. Numbers. Negative exponents. Okay. This, putting things into perspective here, this is actually a video, and I'm just going to start it here, and just so you can kind of see what's going on with it. But this video, if you download the PowerPoint slides as a file, and don't print them out necessarily, but you're certainly welcome to. But if you download that file and you click on this black box here in the file, it will play this video, which kind of puts things into perspective and talks about really large numbers and really small numbers. This video is somewhat dated. This was produced, I believe, in like 1978 or something like that. And it talks about really the effect of you're adding another 0 and going up by powers of 10. So I'm not going to play the whole thing, but you're welcome to play that. And I think I'll put a link on Blackboard to this as well, so if you want to see it again, you may. Alright. So scientific notation is a way of keeping track of zeros. It's a convenient way of expressing really large numbers or really small numbers. Now we had just talked about powers of 10 before, but scientific notation has two parts. It has this coefficient, 1.23456.7, and then a times 10 part, or a power of 10 part. So there's two things here. Notice proper scientific notation, you've only got one digit to the left of the decimal place. So 6.543 times 10 to the third. There's only one number to the left of the decimal. That's this 6 here. All right, just one number or one digit to the left of the decimal. These two numbers, 6.543 times 10 to the third and 65.43 times 10 to the 2, these are numerically equivalent. Right? But this has two digits to the left of the decimal, and it is incorrect or wrong. And when we start talking about using your calculator is smart enough to always put it into proper scientific notation. But if you write it like this on the test, you're going to lose a point because you need to move this decimal over one spot over here between the 6 and the 5. Okay? As I mentioned before, large numbers have positive exponents. In that video, they talk about the diameter of the solar system. It's 1 times 10 to the 13 meters. This is 10 trillion meters. Okay, small numbers, really small things, such as maybe the diameter of a DNA molecule, is 1 times 10 to the negative 7 meters. That's 0.1 millionth of a meter. And negative numbers, or negative exponents, small numbers, positive exponents, large numbers. You should learn to convert between scientific notation and decimal form. You don't always have to use scientific notation. My rule of thumb is if the exponent is greater than 3, or maybe less than negative 3, 3, 4, 5, then use scientific notation. But if it's 12.45, you don't need to, use scientific notation for a small number like that. But when the exponent gets around 3, on the order of say 4 or 5 like this, then use scientific notation. Okay, so we've got a couple numbers here in scientific notation. We want to convert those, say, to decimal form. This times 10 to the 4, what that 4 means is we're going to move the decimal place 4 decimal places over. So this would be 1 decimal place, 2 decimal place, 3 decimal place. I'd have to move it over 1 more place. Okay, 4 decimal places. Now, you could obviously move it in two directions, either to the right or to the left. But if you think about it, remember, this is a positive exponent, so it's a large number. So I want to convert this to a large number. I'm going to go from 2 to 20 to 200 to 2003. I don't want to go the other way and make it 0.2. I want to make this a large number. So I'm going to 0, 0, 3, 0. Right. So the decimal was here, and then we go 1, 2, 3, 4 places. Put the decimal there, and we get what? This is 20,030. Okay. Now let's look at 3.14. 3.14 times 10 to the negative 2. Right. Negative 2, this tells me it's a small number, so I'm not going to convert 3.1 to 31. I don't want to go to the right. I want to go to the left. So I'm going to put a couple zeros out here. And what I want to do is move it 2 places over. 1, 2. And what does this become? 0.0314. Okay, so this is a fraction. It's less than 1. I have a negative exponent. Do the same thing here. Now negative 5. So we're going to have to put a bunch of zeros in here. 5 zeros. I'm going to put it 1, 2, 3, 4, 5. Why am I putting it on the left-hand side? Well, it's a negative exponent, so I'm going to go from 5 to 0.5 to 0.05 and keep going. All right. So we moved it 1, 2, 3, 4, 5 places, and the value I get is 0.000123 4. I think that's 5, right? 1, 2, 3, 4, 5. Oops, that's a 5, 6, 3. Okay. 8.98 times 10 to the 6. 10 to the 6 is a million. A 1 with 6 zeros. So this is a big number. 8, 9, 8. I'm going to put in a bunch of zeros here. 1, 2, 3, 4. Okay. So the decimal was here. And I'm going to move it 1, 2, 3, 4, 5, 6. And the value I get is 8,980,000. That's the decimal. Okay. So this is just practice for you. So what I ask you to do maybe is pause this video and work these examples, and then restart the video and see how well you did. Okay. So go ahead and pause it now and work on these. And when you restart it, I will explain how we get around to putting these in scientific notation. So we only want 1 digit to the left of the decimal. So we're going to put the decimal here. it's going to be 1.4530. The decimal was here, and I moved it 1, 2, 3, 4 places, so times 10 to the 4. Here we only want one non-zero number to the left of the decimal, so I want the coefficient to be 1.45, and I moved the decimal 1, 2 places over, so times 10 to the what? 10 to the 2? No, this was a fraction. It was less than 1. Fraction, small numbers get negative exponents, so negative 2. Right. Similarly here, this is going to be 3.89. And we move the decimal 1, 2, 3 places over, so times 10 to the negative 3. And lastly, we want the decimal there, so it's 3.362 times 10 to the what? Well, the decimal is here, and we move it 1, 2, 3, 4, 5 places. It's a large number, so it gets a positive exponent, 10 to the 5th. Right. So you should be able to convert from decimal form to power of 10, and this is what we just did, and also backwards from power of 10 to decimal. This doesn't do us any good unless we can do some calculations with it, so let's talk about multiplying and dividing numbers in scientific notation. Okay. There's 2 steps when you multiply numbers in scientific notation. The first thing you do is you multiply the numbers. Okay, so multiplying numbers in scientific notation, we're going to multiply the coefficients. We handle the coefficients and the exponents separately, so we're going to multiply 1.34 by 3.56. So we'll just do that calculation, 1.34 times 3.56. And the number we get is 4.7704. 4.7704. You get a bunch of other numbers too, and you might be wondering, well, geez, how many numbers do I need to keep? Do I keep all of them? Do I keep 3 of them? Do I keep? Well, I'll tell you what. That's kind of a different concept coming in a different lecture. So for right now, don't worry about it. But you multiply these 2 numbers together here, and then what we do is we add the exponents. Right? So times 10 to the what? Well, we've got 3 plus 8 is 11, right? So it's going to be 4.7704 times 10 to the 11th. Why do we add the exponents? Well, if you think about it, 10 times 10, we said, is 100, right? Which is what? That's the same as 10 squared. Well, 10 is the same as 10 to the 1. That's weird. My ink just changed color. This is 10 to the 1 times 10 to the 1. 1 plus 1 is 2. So it works out, right? So we add the exponents. 2.77 times 3.45 gives me, let me use a different color here, gives me 9.5565. Again, don't worry about how many decimal places to keep. We'll talk more about that later. Times 10 to the what? Well, notice we've got a negative 3 here, so it's negative 3 plus 6. What's negative 3 plus 6? We're starting off at negative 3. And if you have to, probably don't deal with negative numbers too often. It's supposed to be a number line, more of a number curve. So here's negative 3, here's 0. 1, 2, 3. And we're going to add 6 to this. So we're not starting off at 0, right? We're starting off at, or 3. We're starting off at negative 3. We add 6 to it, we get to positive 3. So we get 9.5565 times 10 to the 3rd. This last one here, 4.88 times 5.99. This is interesting. It gives us a value of, this is essentially almost 5. 4.88 is almost 5 times almost 6. So we get 29. 29.2312. 29.2312. Oops, that's not a decimal there. 29.2312. All right. That's the coefficient. What about the exponent? Times 10 to the what? Here again we've got negative exponents. Negative 6 plus a negative 4. Okay, so again, up at this number line here, right, we're starting at negative 3. Oops. Negative 3, negative 4, 5. Negative 6. and we're going to add to that not a positive 4, which would carry us closer to 0, but a negative 4. Negative 6 and negative 4 is negative 10. So we get 29.2312 times 10 to the 10. Okay. Now there's an issue with this number because it is not in proper scientific notation. Had you been using your calculator, and we'll show you how to use your calculator to do this math later, it would have automatically, your calculator would have automatically put it in proper scientific notation. But if you do it this way, you're going to have to move this decimal place over like this. So we went from 29 to 2.92312. Now we can't simply change 29 to 2.9 and expect that that's okay. But what we're going to have to do then is compensate by changing this exponent. So if you notice, we went from 29 to 2.9. The coefficient, this number before the power of 10, got smaller by 1 decimal place. So it got smaller. Oops, and I almost forgot, this is not 10 but a negative 10. Very important, negative 10. Okay, negative 6 plus negative 4 is negative 10. So the coefficient got smaller. So what happens to the exponent? It's going to get larger. It's going to get larger by 1 power of 10. So what's 1 more than negative 10? Think about your number line here. What's 1 more than negative 3? It's not negative 4, it's negative 2. Right? So here, 1 more than negative 10 is actually negative 9. Okay, so to put in proper scientific notation, you have to move this decimal place over, and for each place we move it over, if it gets smaller by a power of 10, then this exponent has to get larger by a power of 10. So you can kind of think of it as a seesaw or a teeter-totter, right? If this end goes down, this end goes up. And we end up with two numbers that are numerically equivalent, but this number down here on the bottom is in proper scientific notation. Okay. Dividing numbers in scientific notation. All right. Division and multiplication are kind of opposites. So first thing we do is, well, we divide the coefficients and then we subtract the exponents. All right. So 6.34 divided by 3.56 gives me 1.78089, I think, is what I wrote down here. Now, again, don't worry about how many decimal places we need to keep. That's a different lecture. We'll talk more about that later. And then the power of 10 part times 10 to the what? It's going to be 3 minus 8. You can think of this fraction bar as our division symbol, right? Just as 1/2. What is 1/2? This is 1 divided by 2. 1 divided by 2, the numerical equivalent of 1/2 is 0.5, right? So we're not going to ever use the division symbol. Instead, we write them as fractions like this. Okay, now then, 1.78089 times 10 to the 3 minus 8 is what? 3 minus 8 is a negative 5. So it's 1.78089 times 10 to the negative 5th. Next one, 2.77 divided by 3.45 gives me 9.5565 times 10 to the what? Well, we're going to subtract the exponents again. Negative 3 minus 6. Negative 3 minus 6 is what? A negative 9, right? Remember, this is 0, negative 3, 4, 5, 6. So we're going to add, or sorry, not add, we're going to subtract from negative 3, and we get to negative 9. So this becomes 9.5565 times 10 to the negative 9. Last one here, 4.88 divided by 5.99 gives me 0.8. What did I just do? This is an error. I think I multiplied these guys. Let me erase that. The exponent is right, but this coefficient is not. Coefficient should be 0.0829. 0.0829. 0.0829. No, that's wrong too. It's 0.8029. 0.8029. Okay, that looks better. All right, so there's an issue here again. We've got the coefficient right finally. We've got our exponent, but this is not in proper scientific notation, so we're going to have to move the decimal this way. We want one non-zero number, 1, 2, 3, 4, 5, 6, 7, 8, 9, something other than 0, to the left of the decimal. So this is going to be 8.029 times 10 to the what? Well, what happened here? We went from 0.8 to 8. So here the coefficient got larger. That means our exponent must get smaller. What's smaller than a negative 9? Remember our number line here, negative 9. Say this is negative 9, we want to get smaller, we want to go away from 0, so it's going to be negative 10. All right. 4.88 divided by 5.99 gives me 0.8147. 0.8147. Again, we've got a fraction here. All right, we're going to have to move that decimal place over. What is the exponent going to look like? It's 10 to the negative 6 minus a negative 4. So remember when you were a kid and your mom taught you that 2 wrongs don't equal a right, but then you went into math class and they said 2 negatives equal a positive. So I could rewrite this, put it over here. Negative 6 minus a negative 4 is the same as negative 6 plus a positive 4. Right? So we get 0.8147 times 10 to the what? Negative 6 plus a positive 4 is going to get us to a negative 2. And then again, if we put this in proper form and move that decimal over, I get 8.147. So I've got just one digit to the left of the decimal, times 10 to the what? Well, the coefficient got larger, went from 0.8 to 8. So this exponent gets smaller. We go from negative 2 to a negative 3. Okay. Hopefully you have a scientific calculator. You're going to need one for the test. There is no borrowing of calculators on a test. You can't share a calculator. You need to come to class with a working calculator. You cannot use your cell phone during taking of a test. So make sure you have one. And if you're not sure if it's scientific or not, what you're really looking for is a button like this here, this EE. This EE button, or it might say SCI here. I don't know if you can read that, but it says SCI above the 5 here. That's what you're looking for. Okay. So to enter numbers in scientific notation, say we wanted to enter a number 6.02 times 10 to the 23 in our calculator. You enter the coefficient 6.02. The display on your calculator will read 6.02. Then you press the EE, or maybe it's an EXP button, or maybe an SCI button, or sometimes it's even a 10 to the X button. I've also seen it that way as well. Sometimes it's a 10 to the X button. Okay, and then what you get is a couple zeros off to the right. You notice in this display here, this superscript 99, that's the exponent. So this is 1.2345 times 10 to the 99. So once you press this button, you'll see a couple zeros off to the right. You may even see a times 10 in there, maybe it's just a couple zeros, or maybe it's actually an E and then a couple zeros. All right? So when you press that EE, EXP, or SEI button, you are taking into account this times 10. When you enter a number in scientific notation, under no circumstances do you ever press the multiplication symbol and then 10. And it's really easy for me to find out if you did that because all your answers are going to be off by 1 power of 10. So when you're entering numbers in scientific notation, this EE, EXP, or SEI button takes care of the times 10 part. All you need to do then is put in the exponent. So the next thing we would do is enter 23, and the display word is 6.02, and then off to the right it'll say 23. So this EE, EXP, or SEI button takes care of that times 10 part, and then you simply enter in the exponent. So get some practice with your calculator doing that sort of thing. What if we had a negative exponent? Well, very similar. Enter the coefficient, 1.16, the display reads 1.6. Press your EE or SEI button. Now we have the zeros out here. These two, the next two steps here, these two, it kind of depends on your calculator. Some calculators will ask you to put the negative sign in first. Some calculators ask you to put the 19 in first, and then you press the change sign button or a minus sign to change that. That change sign button, this plus minus sign here, sometimes it will be drawn as something like, you'll see a button that looks something like this, where you convert between the plus and minus. Okay? So first thing you'll do is enter the number. If you're doing a calculation, you enter the number in scientific notation, press 4.55, press your EE or EXP button, enter a 3. We're not messing with the 10. That was already done when we pressed the EE button. Enter the exponent 3, and then the times symbol. I'm going to put a times symbol here. Press the times button, enter the next number, and then press equals. Press the equals button. And what do you get? So 4.55 times 10 to the third. Enter that number, press the multiplication symbol, enter the next number, press the equal sign, and you should get 1 point. Here's 1 point. It's a 3. 1.356. 56. Come on now. Times 10 to the 13. And if you're looking here and you're thinking, well, wait a second. I thought we were supposed to add the exponents. 3 plus 9 is 12. Why does it say 13? Well, that's because 4 times 5, or 4.55 times 3 is actually 13.56, but your calculator was smart enough to put it in proper scientific notation and move that decimal place from 13 to 1.3 and make the exponent larger. All right. Similarly here, we have enter the first number, 5.08 times 10 to the 6th. Press the division symbol. This fraction bar is our division symbol. Divided by 1.22 times 10 to the negative 8. And we should get 4.1639 times 10 to the 14th. Okay, back up. All right, so practice on this. You've got some homework that deals a lot where you're going to repeat a number of these types of calculations. Get some practice. Make sure you know how to use your calculator. If you have any questions, be sure to email me or ask me at the start of class. Next, this question here is messed up. I have the numbers reversed. It should be 4 miles in 12 minutes. Okay, 4 miles divided by 12 minutes, that's 1/3, so we get 0.333333 repeating. How many of these 3's do we need? All right, that's the next lecture entitled Sig Figs. What's a sig fig? Stands for significant figures or significant digits, and that will be the next recorded lecture. Thanks for your attention. Good luck.